Hello everyone, welcome to CE4390 Chapter 4 Loading and Hauling. In this video, you will learn how to design a hauling operation with trucks as a hauling unit. Okay, let's see what are the learning objectives. First, you need to understand the necessity for balance between the excavator bucket volume and the truck load volume. In other words, you need to understand the importance of selecting right trucks for your project, why the truck size matters, and what are the problems if you choose too big or too small trucks. Second, ability to use performance charts to calculate truck speed. You have seen this kind of chart before in previous lessons of this chapter. This is called performance chart, which we can use to balance the speed. Which we can use to calculate the speed of the equipment. Today you will learn how to use this performance chart to calculate truck speed based on the truck weight and the resistance grade. Third, ability to calculate the number of trucks required to keep excavating equipment working at its capacity. Let's say you decided to use one excavator for your project. The next question that you need to answer is how many trucks that you need. How many trucks that can maximize the efficiency of the excavator as well as the trucks. And finally, the ability to estimate costs by evaluating equipment balance. You need to know how to calculate how much it costs for using trucks and excavators so that you can balance the numbers of trucks and excavators and then determine the number of trucks that is most economical. Okay, you know that there are other types of machine that can be used for all hauling. So why do we use trucks and when should we use trucks? Remember from chapter 4.4, the selection of hauling units is mainly driven by the hauling distance. So this figure gives you a guidance on what type of hauling units to be used given different hauling distances. Again, for short distances we use dozers and loaders. For longer distances we use scrapers or articulated trucks. For extremely long distances up to 35,000 feet, it is more economical to use rear dome trucks. Section 1, Introduction to Truck. So as you saw in the video, there are many different types of trucks. We can classify trucks by the location of operation. So we got highway, on highway and off highway trucks. Based on the methods of dumping, we have rear, bottom, and side dump. Regarding the types of engine, we got gas, diesel, and hybrid engines that use both diesels and electrics. For transmission mechanisms, we got mechanical transmission or diesel electric. Truck can be also used for construction or mining. So we have mining trucks and construction trucks. And finally, we can classify trucks based on capacity, which can be measured by the weight or the volume. Weight could be in pounds or tons, and volume is usually in cubic yards. Section 2, capacities of trucks and hauling equipment. Hauling capacities are rated in at least 3 methods. Number 1, weight. So using these methods, the recommended maximum load, usually in pounds or kilograms, will be given. Number 2, stock volume. So this method measures the volume usually in cubic yards. It is the total volume when assuming that the load is water, so it is level off at the top of the box. Number 3, heap volume. So this is the total volume considering the material that is heaped on top of the box. We typically assume a 2/1 slope for the material portion above the box. So these two figures show different types of volume. The one on the left is stroke volume. As you can see, the material is flushed off across the top of the body. And the figure on the right side indicates the heap volume. The soil is heaped above the hollow body, and the soil slope is typically assumed to be 2/1. Caterpillar Performance Handbook 47 gives you the rated capacities for many models. So this table here is one example taken from the handbook, page 12, and here are the rated capacities for the models 725 C2. The maximum weight is 26.5 tons. Stroke volume is 14.4 cubic yards, and the heat volume is 19.6 cubic yards. To extend the life of the equipment and to avoid any accidents, many manufacturers, including Caterpillar, providing a loading management policy that gives you some guidelines on how to load the equipment safely. You can see the details in the Caterpillar Performance Handbook 47 in page 1623. Here I list some typical requirements within any 30 days period in which the truck is used. No more than 10% of load should exceed 110% of the rated payload. It means sometimes you can overload the equipment, but it shouldn't be too often. Also, no loads should exceed 120% of the rated payload. You can overload it up to 120%, but you should never put more load than that limit. Another requirement is the average of all the loads for the units within a 30-day period must at least equal to the rated payload. So those are the requirements that you can use to extend the life of the equipment and to avoid any accidents. So this figure is the recommended distribution of all the loads within a certain 30-day period. The load should be ranging from 80% to 120% of the rated capacity, and it must be above 80% so that you can maintain the desired productivity, and it cannot be above 120% of the target payload due to the safety concern. Also, to avoid consistent overloading, which is not good for your tires, the number of times that the truck is overloaded above 110% of the capacity must be less than 10%. Komatsu, which is a Japanese equipment maker, has a similar policy, except that the last item states that the average monthly payload must not exceed the rated payload of the truck. So carrying more than the recommended payload abuses the tires, and since the tire costs account for about 30% of the truck's operating costs, so you want to extend the tire life as much as possible. Section 3, Truck Performance Curves. So this figure is one example of performance curves. The top axis is the weight of the machine, including the load, and the bottom axis indicates the speed. The right vertical axis represents the total resistance in percentage. E indicates the empty truck weight. L refers to the total weight when the truck is fully loaded, and the input that you need include the total weight and the total resistance. So with these two information, you can calculate the maximum speed. Now I'm gonna show you how to use this chart to find the speed. First step, you need to find the inclined line corresponding to the total resistance. So let's assume a total resistance of 20%. Next step, you draw a vertical line at the total weight. So let's assume that the truck is empty, so the vertical line is exactly at the E line. Now you find the intercept between these two lines. At the intercept, you go horizontally until you meet the gear curves. Then you go vertically down to identify the speed. So in this case, it is around 11 mile per hour. So when the truck is loaded, you need to find the intercept between the L line and the 20% resistance line. So you repeat the process, you can get the maximum speed of around 5 miles per hour. So this performance chart has a different format than the previous one. So this chart is for truck terrace T8250. So in this chart, the weight and the resistance are in a separate diagram on the right side. So where the weight axis is on the lower horizontal edge, and the process should be the same. First, you need to identify the resistance line, let's say 12%. Then you make the vertical line at a certain vertical weight. Next step, you go horizontally to the gear curves, and finally go vertically down towards the speed axis to find the maximum speed. So like what you have learned for other machine, we also use retarder performance curve when the machine goes downhill with a negative total resistance. So this chart shows an examples of retarder curves for trucks. To find the maximum speed, you can follow exactly the same procedure for performance curves. And the curves in the next slides are for Komatsu HM302 trucks. Its capacity is approximately 30 tons. Again, these curves are for HM302 trucks. To identify speed, you can do the same process. Section 4, a truck production cycle. So you can see the definition of truck cycle in Caterpillar Performance Handbook 47, page 1020. The truck production cycle includes number 1, load, number 2, exchange. It refers to the maneuver time in the loading area. Typically, it is about 0.6 to 0.8 minutes. Number 3, haulings. Number 4, maneuver and dumping. So this time component is typically ranging from 1 minute to 1.2 minutes. Number 5, return. So those are the 5 time components of the truck production cycle. So this figure illustrates the production cycle of trucks. As I said, it includes loading, hauling, maneuver and dumping, return and exchange to the loading area. The total cycle time will be the summary of all these 5 times components. Okay, so how to estimate these cycle times? Okay, for hauling and return times, we can determine using performance or retarded curves as explained earlier, and also remember that we need to adjust the maximum speed for acceleration and deceleration as we did for scrapers. Okay, for load time, it is dependent on um, the size of this excavator bucket and also the capacity of the truck. Small excavator need more time, and it will take you more time for loading if you're using trucks with a larger capacity. To calculate load time, you multiply the number of buckets loads with the cycle time of the excavator. Here, the number of bucket loads refers to how many cycles that the loader must perform until the truck is full. Exchange term and maneuver terms are fixed time, and it can be estimated using table 49 in your textbook. I will explain this table later when we do an examples. Caterpillar Performance Handbook 47, page 1020 gives you the following typical values for fixed terms. 0.6 to 0.8 minutes for exchange times and 1 minute to 1.2 minutes for maneuver and dumping time combined. Okay, load time. As noted earlier, load time depends upon the number of bucket loads to fill the truck. So how to calculate the number of bucket loads? What you need to do is to take the truck capacity, then divide it by the bucket capacity. For example, if the truck is 20 tons, the excavator bucket is 5 tons, and that means the excavator needs 4 cycles or 4 bucket loads to fill the truck. So here are several rules of thumb when you select in the number of bucket loads. For mining, it is more economical to have 3 bucket loads per truck. Don't use more than that. For construction, it is slightly higher, ranging from 4 to 6 passes per truck. The number of bucket loads to fill the truck must be an integer number. Therefore, it will almost always need to be rounded. For example, if you got 4.3, you need to round it up to 5 or round it down to 4. So what happens if you round it down? The truck will not be filled to its capacity, but the loading can be complete faster. If you round it up, the truck is filled to capacity or over. What do you think about this? So let's see the answer in the next slide. So if you round it up, there are 2 options. The first option, the last bucket load will not fill to its capacity. The second option, the last bucket is full and the excess will spill out of the truck. Section 5, truck production estimating format. So now I'm gonna show you how to estimate production of truck using the following examples. So in this example, we have 10 28 tons or 19 cubic yard rear dump trucks available to haul sand and gravel mixtures, which has a unit weight of 2,900 pounds per load cubic yards, and the empty vehicle weight is 51,000 pounds. The performance curves below apply for this machine, and the wheel loader being used has a 4.5 cubic yard bucket. And the haul and return over poorly maintained earth, which has a distance of 3 miles, and it is downhill grade of 1.5 25% going to the dumping area. It means when the machine is going back from the dumping area, it's gonna be negative 1.25%, and the working hour efficiency is 50 minutes per 1 hour, and the loader cost is $125 per hour, and each truck costs you $75 per hour. And this is the performance chart of the truck in this example. Okay, step number one, calculate the number of bucket loads to fill the truck. To calculate it, you need to know the truck capacity and the bucket capacity. From what given, we got 28 ton or 19 cubic yard truck, and the material is sand and gravel mixture. The loader bucket is 4.5 cubic yards. Um, Remember that we need to adjust the bucket volume using the fill factor corresponding to the material type, so we can use table 3.2 to find the fill factor. So given sand and gravel mixture, the bucket fill factor is gonna be ranging from 0.9 to 1, so let's use the average value, which is 0.95. To calculate the bucket capacity, you multiply the bucket volume 4.5 cubic yard by the fill factors 0.95, so we got 4.28 cubic yards. Now we calculate the bucket loads. It is equal to the truck capacity 19 loads cubic yard per truck divided by the bucket volume 2.28 loads cubic yard per bucket. So we got 4.44 buckets per trucks. So should we use 4 or 5 bucket loads? So if you use 4 bucket loads, the total truck load volume will be 4 times bucket volumes 4.28 or 17.1 loads cubic yards. So if you're using 5 bucket loads, the truck volume is gonna be 21.4 loads cubic yards. So this is more than its capacity. Remember that the truck capacity is 19 loads cubic yards. So let's assume that the load is 19 loads cubic yards and the excess will spill off the truck. So next we need to check the weight limit. So we need to check the load weight against the weight capacity of the whole unit. So with 4 buckets, the truck volume is gonna be 17.1 loads cubic yards. To calculate the weight, you multiply it by the unit weight of the materials, 2,900 pounds per cubic yard, and divided by 2,000 pounds per tons to convert pounds to tons, and finally you got 24.8 tons. So this is less than the rated weight, which is 28 tons, so it is okay. So with 5 buckets, the truck volume is 19.1 loads cubic yards. So you do the same process and you got 27.6 tons is still less than the given weight capacity of 28 tons, so it is okay. Step number 2, determine the loading time, or the time it takes the loader to fill the truck. So it is equal to the excavator cycle times multiplied by the number of bucket loads. Since the excavator cycle time is not given yet, so you need to calculate it using table 4.6. So this is table 4.6. Assume that the average loading condition, and given the wheel loader, the basic cycle time of the loader is gonna be 0.5 minutes. So if you use 4 buckets loads, the total loading time is gonna be 4 times 0.5 or 2 minutes. So if you use 5 bucket loads, it is 2.5 minutes. Okay, step number 3, use total resistance and performance curves to determine travel speed and then haul time. To calculate travel time, you divide the distance in feet by 88 and the speed in mile per hour. So in these examples, the distance is given as 3 miles. Again, we will use performance chart to calculate the speed. So you need the total resistance and the total gross vehicle weight. So total resistance is equal to rolling resistance plus grade resistance. So first let's find rolling resistance using table 4.1. Okay, to use table 4.1, you need to know the types of surface. In this example, the trucks travel over poorly maintained earth. So you need to look up the dirt surface in this table. So these two are more close to our hauling condition. So let's use the average of the rolling resistance factors for these two conditions. So it is 125 pounds per ton. So next we need to convert it into equivalent percent grade. So you divide it by 20 pounds per ton per percent. So you got 6.25%. And next you need to find the grade resistance. So as given, the hauling grade is downhill. It is negative 1.25%. So the total grade is equal 6.25 plus negatives 1.25 or 5%. So this is for haul direction. So we will calculate the total grade for return direction later. Another thing that you need to calculate is the total gross vehicle weight. As given, the empty weight is 51,000 pounds. So you need to add it by the weight of the load. Remember that we don't know how many bucket loads yet. So if you use 4 bucket loads, as we found earlier, the total weight is 24.8 tons or 49,600 pounds. So the gross vehicle weight is the sum of empty weight 51,000 pounds plus the total load weight 49,600 pounds. So you got 100,600 pounds. If we use 5 bucket loads, you repeat the same process, you can get the total gross vehicle weight of 106,200 pounds. Okay, let's use the performance chart to calculate speed. With 4 bucket loads, the total weight is 100,600 pounds. The total resistance is 5%, so the speed is around 18 miles per hour. With 5 bucket loads, the GVW is 106,200 pounds. The resistance grade still 5%, and we got the speed about 17 miles per hour. So 1 mile per hour less than the speed with 4 buckets. So remember that those speeds that we found earlier are the maximum speed. Now we need to find the average speed for the whole section using table 4.3. Given a hauling distance, so this table gives you the factor, the speed factor. In this example, during hauling, the truck needs to accelerate from 0 to the maximum speed, then it decelerates to 0 when it stops. So we use this column to find the speed factor. Note that the speed factor becomes significant only for short hauling distances. Up to 5,000 feet, the speed factor is close to 1. In other words, the average speed is equal to the maximum speed. So in this example, the distance is 3 miles or 15,000 feet, which is far above 5,000 feet. So let's use a factor of 1, which is close enough. So with 4 buckets, the speed is 18 miles per hour. To calculate travel time, you divide the distance 3 miles by 88 and the speed 18 miles per hour. And here you multiply the distance by 5,280 to convert mile to feet, and you got 10 minutes. With 5 buckets, the speed is 17 miles per hour, so you got the total travel time of 10.59 minutes. Step 4, now you can use total resistance and performance curves to determine travel speeds and then return time. So return time can be calculated using the distance divided by 88 and the speed when it returns. So when return, the truck goes uphill, so the grade resistance is gonna be 1.25%, and by adding the rolling resistance of 6.5%, 6.25% with 1.25%, you got the total resistance of 7.5%. So during return, the truck is empty, so the total weight is 51,000 pounds. So this is given in the problem statement. So now let's use the performance chart to find the maximum speed for return. So we got resistance of 7.5% and the empty weight of 51,000 pounds during return. So the maximum speed is gonna be 21 miles per hour. So remember that we use the speed factor of 1 since the travel distance is large. So the average speed is very close to the maximum speed of 21 miles per hour. So what you need to do is just repeat the process that you did for hauling, and you can get the travel time of 8.57 minutes. Step number 5, determine sport maneuver and dumping time. You can use table 4.9 to calculate the total fixed time, but this table gives you the fixed time excluding the loading time. So assume that the truck is a rear dump truck and the hauling road is poorly maintained, or so it is quite a little bit worse than the average. So let's use 1.6 minutes as a total fixed time, excluding loading time. Step number 6, determine the total truck cycle time. By adding all time components, including fixed loading, hauling, and returning, you got a total cycle time. With 4 buckets, it is 22.17 minutes. With 5 buckets, you got 23.26 minutes at this total cycle time for trucks, and so it takes trucks 23.26 minutes to finish one cycle. Now, step 7, we can determine the number of trucks required. To find the number of trucks, you divide the truck cycle times found in step number 6 by the loading time found in step number 2. So with 4 buckets, the truck cycle time is 22.17 minutes and the load time is 2 minutes. So we got 11.09 trucks. So this is called the balance bond between trucks and excavators. So should we use 11 or 12 trucks? Don't forget that we have only 10 trucks available, so we use all 10 trucks. So that means one excavator serves 10 trucks. So this is below the balance bond. So the trucks govern the production, and there's no idle time for trucks, but the excavator will experience idle time. With 5 buckets, the balance bonds is 9.3 trucks. So should we use 9 or 10 trucks? Remember that the number of trucks available is 10, so either 9 or 10 should be okay. But you need to choose the number of trucks that is more economical. So you need to compare the cost per cubic yard between two options. To calculate this, you need to know the production for these two options. Step number 8, determine production. So similar to what you do for scrapers, to determine production, you need to know what equipment controls the operation. If the number of trucks is above the balance bond, so what governs the production? It is loader. And the production of the whole system is controlled by the production of the loader. So how to estimate production of the loader? So this is the equation that you learned in previous lessons of this chapter. It is equal to the number of bucket cycles per hours multiplied by the bucket volume. However, don't use this equation since the production is also determined by the truckload. So this equation may result in the production which is greater than the truck capacity. For this reason, you need to calculate the ideal production by multiply the number of truckloads by the truck volume. So in this equation, the loader cycle time refers to the total load time per trucks as found in step number 2, and the truck volume is the actual load volume. It is not the truck capacity. The load volume is found in step number 1. If the number of trucks is below the balance bonds, trucks will control the system operation. So the production is equal to the number of cycles that a truck performs per hour based on the truck cycle time found in step number 6 times the truckload volume, and then times the number of trucks. So let's get back to the examples. With 4 buckets and 10 trucks, it is below the balance bonds. So trucks control the production. By applying the formula for the situation when the number of trucks is below the balance bonds, we got the production of 463 loose cubic yard per hour. For 5 buckets, we have 2 options to consider. First, 9 trucks. Second, 10 trucks. So if you choose 9 trucks, it is below the balance bond. Applying the equation when the number of trucks is below the balance bond, you got 60 minutes divided by the total cycle time of the truck, 23.26 minutes, and then times the total load volume, which is 19 loose cubic yard per truck, and then finally times 9 trucks, you got the production of 441 loose cubic yard per hour. So if you choose 10 trucks, it is above the balance bond. And now you apply the equation when the number of trucks is above the balance bond. You got 60 minutes per hour divided by the load time of 2.5 minutes, and times the load volume of 19 loose cubic yard per truck. So this is equal to 456 loose cubic yard per hour. Step 9, apply the efficiency considering bunching, operator, equipment availability. But let's see what reduces the efficiency of the trucks. Bunching is the most common factors that has a significant negative impact on the efficiency of any construction operation. And it is the situation when many hauling units arrive at almost at the same time. So this leads to significant waiting time for all the trucks. So with a perfect loader and hauler mesh, for example, at the balance point when the number of haulers perfectly matches with the loader capacity, research show that bunching still happens, and it causes 10% to 20% production loss. Um, so this is due to the uncertainty of the travel time. Travel time is not always constant. So if there are extra haulers, the bunching effect is reduced because there is always a line of trucks waiting to be loaded. So the loader will work all the time and no idle time for the loader. Similarly, if there are insufficient number of haulers, the bunching effect is also reduced because the haulers are unlikely to have any wait time. So let's see how the production is related to the number of haulers. So this is the loader capacity line. The production of the whole system cannot exceed this limit. So when you increase the number of haulers from 0, the production will increase until it reaches the loader capacity. So this bond is called balance bond. The truck production cannot exceed the loader capacity. And after this bond, the production lines will go horizontally. No increase in production even though you increase the haulers. So this curve represent the bunching effects given different number of haulers. As I said, research shows that at the balance bond, the bunching effects is maximized. It is about 10% to 20% loss in efficiency, and this effect is reduced either reducing or increasing the number of haulers. So in this example, as given, the efficiency is 50 minutes. You are not required to calculate it. And in this course, we are not covering how to calculate efficiency. Since the work hour was given as 50 minutes, so we got 50 minutes per 60 minutes, or 83% efficiency. So let's summarize the production calculation. With 4 buckets and 10 trucks, the ideal production is 463 loads kpg. So if you call this column as A, the production after considering the efficiency is gonna be A multiplied by the efficiency of the 83%, so which is equal to 384 loads kpg per hour. So with 5 buckets in 9 trucks, we got an ideal production of 441 loads kpg, and the adjusted production is 366 loads kpg. And finally, with 5 buckets and 10 trucks, we got 456 and 378 loads kpg. So of those 3 options, what do you use? To make that decision, you need to calculate the cost for each option. So in step 10, you need to determine the cost per cubic yard. Why matching the fleet to the required production is important, but it may be costly. So doing earthwork at a minimum cost per unit of material is usually the goal. You want to minimize the cost for the whole project. Okay, let's see what given information that we can use to calculate costs. First, we got the loader cost $125 per hour, and also we got each truck cost $75 per hour. So now let's calculate hourly costs of the whole fleet. See, if we use 9 trucks, the hourly total cost is equal the hourly cost of the loader $125 per hour plus the hourly truck cost of $75 per hour and times 9 trucks, because we have 9 trucks, and then we got $800 per hour. So if we use 10 trucks, the total cost is going to be $875 per hour. So those are the hourly costs. Next, you need to calculate the cost per unit of the material so that we can compare different options. So option 1, 4 buckets and 10 trucks, the unit cost is equal the total hourly cost $875 per hour divided by the production 384 loads kpg per hour, which we found in step 8, or the unit cost is equal to $2.28 per loads kpg. Now you need to repeat this process for the other 2 options with 5 buckets. With 5 buckets and 9 trucks, the unit cost is $2.19. And the third option, 5 buckets and 10 trucks, we got $2.31 per cubic yard. So now you can compare these 3 options, and we choose 5 buckets and 9 trucks because it requires least unit cost. So that's the end of this video. Now you need to review this lesson one more time and then finish all the homework problems. Goodbye for now and see you next time.